Dial go up about 5, 6, 7 times normal background. That's because the radium in this watch is emitting gamma rays that penetrate that. This is why they don't make these watches anymore. People would fall asleep by their brain, and it's not a good thing. But that's an example of a gamma ray. Now, in the news, you'll be reading about over Tokyo, the radiation levels went up. And what that means is that a cloud of radioactive daughter products, usually xenon and krypton, will pass over Tokyo, and they'll create gamma rays. And that's what's usually being picked up on these personal dosimeters. Now, there's two other kinds of particles that cannot penetrate my detector, and those are beta particles and alpha particles. They get into your body by breathing, or by taste, or through a cut in the skin. And they're when these guys are all bundled up in their suits, that's what they're being protected from beta particles and alpha particles. Now, these particles cause cellular damage only when they're inside you. Iodine, for instance, is selectively absorbed by your thyroid and causes damage directly to the thyroid. If iodine is outside you, it won't really cause radiation damage. The same with cesium. Cesium is exactly like, is absorbed by muscle. And it causes damage, especially to heart muscles in infants, but it causes muscle tumors. And strontium is another beta emitter, and it goes to your bone and can cause leukemia. Again, it's got through your skin, and it's right up against the marrow of your bone, which can cause a leukemia. And the last kind of radiation is an alpha particle. An alpha particle is the biggest and most massive of them all. And it usually comes from depleted uranium or from plutonium. And it's like a howitzer. It's really, really a powerful particle once it gets in your body. If you breathe in these alpha particles, if you breathe in the plutonium, when it decays away, it produces a cancer in your lung. And is very, very damaging. 3 more things before we go today is how radiation is measured. Well, they measure it in something called becquerels, and that's a disintegration per second. 1 disintegration per second is a becquerel. So I'd prefer to call it disintegrations per second. Now you'll see field measurements as far away from Fukushima as 30 or 40 miles, where a piece of paper laid on the field that's a meter by a meter, 3 feet by 3 feet, will pick up 900,000 disintegrations per second of beta particles, or of beta emitting particles, or of alpha emitting particles, or gamma emitting particles. Now, they don't know what that particle is, but they know that the piece of paper has that much on it. That's a lot. You'll also, so a becquerel, when you see that, is a disintegration every second. The other term is a sievert. You'll see 1 millisievert. Well, that's an indication of cellular damage, but the term that I'm used to is a millirem. 1 millisievert is 100 millirem. And so basically it's just 100 times bigger than a millirem. It's a measure of personal exposure. And the last term is half-life. What does that mean? Iodine has a half-life of 8 days. That means in 8 days, half of it's gone. In 16 days, only a quarter of it is left. In 24 days, an eighth is left. So every 8 days, whatever's there, a half disappears. Cesium, on the other hand, has got a 30-year half-life. So you got to wait 30 years for half of it to be gone, 60 years for only a quarter of it to be left, and 90 years for it to be an eighth left. The general rule of thumb is 10 half-lives and it's all gone. So for iodine, in the next 80 days, it will all be gone. But the cesium and the strontium will hang around for 300 years. The worst one of all is plutonium, and if it's released from the fuel, there hasn't been any detected yet, but if it's released from the fuel, it has a half-life of 24,000 years, and so therefore it will hang around in the environment for 250,000 years. Well, that's it for today, and as I see more information on the web, I will try to post it. Thank you. Hi, I'm Arnie Gunderson from Fairwinds Associates. It's Tuesday, March 29th, 2011. Several things in the news have come up in the last several days that I wanted to share my impressions with you. They are the fact that plutonium has been discovered on the Fukushima site. The second, that large quantities of very radioactive water have also been discovered on site. And the last is I wanted to give you my assessment of the condition of the nuclear cores in units 1, 2, and 3. First, the plutonium. Plutonium has been found on 5 different locations on site. And if you remember an earlier video I put together, plutonium is a difficult isotope to detect because it doesn't give off a gamma ray, it gives off an alpha particle, and that's not picked up by the traditional Geiger counters. That plus the high background on site makes it very difficult. So this had to be from soil samples. So 5 soil samples have turned up plutonium. If there's 5, there's more, and that's a great concern for me. Plutonium got its name from Pluto, the god of hell, and it's one of the more nasty isotopes that mankind has ever created. This is a gram. A dollar bill is roughly a gram. Well, if you cut that into 1,000,000 pieces, you have a microgram, smaller than George Washington's eye. 1 microgram can cause a lethal cancer from plutonium. Now, I believe the plutonium is coming from the fuel pool in Unit 4, although you can't rule out the other 3 reactors. Plutonium is evident in all the nuclear reactors. Unit 3 had some plutonium fuel, but all the reactors will have plutonium because the uranium-238 absorbs a neutron and becomes plutonium anyway. So it's in all 4 locations. The reason I think it's in the pool, though, is that it's scattered on the land on the site. And the most likely way to volatilize the plutonium would have been in a fire or a violent Zerk water reaction in the Unit 4 fuel pool. There's still a lot more data that needs to be developed, but again, if you found 5 samples, it's likely there'll be more on site. And a bigger concern to me is that if it's already in 5 locations on site, I think they'll find more off site. And its health consequences should not be downplayed by Tokyo Electric. The second thing is the fact that the enormous quantities of highly radioactive water have been found in trenches. These trenches are outside the nuclear containment. That means the containment isn't containing. I posted a link that's on our site as well that talks about how radioactive material can get out of the nuclear reactor and get through the containment and out into these trenches without a breach of the containment and without a breach of the nuclear reactor. It involves leakage of a seal at the bottom of these nuclear reactors, and it's quite plausible, and I urge you to take a look at it in detail. Well, what does this mean? The amount of water in those trenches is enormous, and it's very difficult to get demineralizers to remove that radioactivity in such high quantities. Basically, if the demineralizer absorbed that radioactivity, it would become so radioactively hot that personnel couldn't go near it. I've also had people say, well, why don't you take that water and pump it back in the nuclear reactor? Well, the radioactivity in that water is over 100 rem per hour. And basically that means that anybody who stands near it for 3 or 4 hours receives a lethal dose of radiation. So if you were to pump it back into the reactor, the pumps would become so radioactive that personnel couldn't operate the pumps. There's not much tankage space available on the site. They're trying to pump that water into the unit condensers The condensers are not seismic and may not have withstood the earthquake and tsunami,